Assessing the relative reactivity of a series of acids or bases is an absolutely essential skill for a student of organic chemistry to have, for a variety of reasons. For one thing, it helps us mentally order acids from strongest to weakest by making comparisons of things that are similar in structure but differ in certain key ways. It helps us identify general trends in structures that lead to acidity or basicity, and we can often bridge the gap from Bronsted acidity and basicity to Lewis acidity and basicity, which is a much broader, much more general paradigm. We have talked about, or will talk about, many of the structural factors that influence the acidity or basicity of a proton. And there are 5 factors that are really the most important when evaluating the relative acidity or basicity of a series or a pair of compounds. A good moniker to remember these is dyslexic Chris, or C-R-H-I-S. And they're listed this way, A, because it's easy to remember, and B, because this is typically the relative importance of the different factors. So the C stands for charge, whether the atom bearing the acidic proton, say, if we constrain ourselves to acidity, is charged or not. And also at this factor we can put the electronegativity of the atoms bearing the hydrogens if they're different. R is resonance, in particular resonance stabilization of positive or negative charges. Delocalization of those charges via resonance tends to stabilize those species, and that can lead to decreased or increased acidity depending on which of the species, the acid or the base, is stabilized by resonance. H is hybridization, and hybridization is an important effect when the hybridization of the atom bearing the hydrogen is different. And the stability of a lone pair in a hybrid orbital plays in there. I stands for inductive effects, which are the influences of electronegative substituents or groups in the vicinity of the hydrogen atom, which pull electron density away from the atom bearing the hydrogen and tend to increase acidity. Of course, the opposite also holds true for electron donating atoms and groups, which donate electron density to the atom bearing the hydrogen. Those groups cause a decrease in acidity. And finally, the S stands for steric effects. Very bulky groups can influence the solvation of positive and negative charges, and that can have an influence on basicity and acidity. When we make comparisons of the acidity of a series of acids, the most important thing to identify is which of these 5 factors is the one that really captures the difference between the molecules in the series. For example, consider the set of carboxylic acids shown here. In all 4 of these molecules, the only hydrogen that we really need to consider is the carboxylic acid hydrogen. This is, in all 4 molecules, the most acidic hydrogen within each molecule. The alkyl hydrogens are not very acidic. To understand why these molecules differ in acidity, though, we need to really focus on where the molecules differ. And structurally, where they differ is in the number and the positioning of fluorines bonded to carbons in each molecule. So in molecule 1, for example, we see a single fluorine bonded to the carbon, which is 1 carbon away from the carboxylic acid carbon. In molecule 2, we see 1 fluorine as well, but this fluorine is actually 2 carbons removed from the carboxylic acid carbon. In structure 3, we see 2 fluorines bonded to this carbon, which is again directly bonded to the carboxylic acid carbon, just like in example 1. And then in molecule 4, we see 1, 2, 3, 4, 5 fluorines bonded to 2 carbons, which are linked through the carbon on the right directly to the carboxylic acid carbon. So where the molecules differ is in the number and positioning of fluorines within the structures. This should be a hint that the dominant factor here really has nothing to do with resonance. We don't see any differences in the distribution of pi bonds or lone pairs that are resonance relevant in the structures. So resonance is out. The hybridization of the atom to which the hydrogen is bonded is the same in all cases. All of these oxygens are sp2, so that's out. Charge is the same in all cases. They're all neutral oxygens, and electronegativity is out since all the atoms are oxygens. And the steric effects, though slightly different since we've replaced, for example, these CH2s with 2 fluorines, really are not that large. A comparison of the size of hydrogen to fluorine will show you that they're actually of comparable size. So steric effects are out as well, and the most important factor here is the inductive effect of the fluorine atom. So let's explore inductive effects in a little more detail to get to the bottom of this. Fluorine is a highly electronegative atom, and that means carbon-fluorine bonds are polarized towards the fluorine. The more fluorines we have, the stronger is the polarization, right? So two fluorines pulling on a carbon are going to make it more partially positive than a carbon pulled on by only one fluorine. So I've drawn the delta plus on the bottom a little bit larger to signify that. And the pulling doesn't just last over one bond. A partial positive charge on one carbon is going to bleed over to some degree to the carbon to which it's attached. So for example, even in the case of molecule 2, where the carbon-fluorine bond causes a partial positive charge on a carbon that's 2 atoms removed from the carbonyl carbon, we should still expect some considerable partial positive charge on this carbon. However, the clear winner in terms of inductive effects is this molecule that includes 5 fluorines bonded to the 2 carbons that are linked to the carboxylic acid functional group. These 5 fluorines put massive positive charge on these 2 carbons and the carbonyl carbon. The last thing to clarify is what's the relationship between the partial positive charge on that carbon and the acidity of the carboxylic acid. Well, remember what an acid is. Keep in mind the general picture of an acid. An acid is something that gives up a proton. So when the group that receives the electrons from the AH bond, in other words, when the A group has very large partial positive charge, well, it's already attracting the electrons from the AH bond to some degree. So structures that have very large partial positive charge within them tend to be attached to very acidic hydrogens. A good example, which uses full charge but really drives the point home, is H3O+. The oxygen atom in H3O+ is formally positive, and thus it has a very strong desire to give up its proton to form neutral water. And that bond, that OH bond, is highly, highly polarized towards the oxygen. So the clear winner then, in terms of the most acidic, is without question molecule 4, which contains the 5 fluorines, all exerting strong inductive effects on the carboxylic acid proton. We can order the acidity of these 4 molecules by considering the relative strengths of the inductive effects, which we've already done to some degree. So we've already concluded that molecule 4 has got to be the strongest acid. But what comes in second? What we find is that the fluorine in molecule 2 is 2 carbons removed from the carboxylic acid group, while the fluorines in molecules 1 and 3 are only 1 carbon removed from that group. So the fluorines in 1 and 3 are closer to the acidic proton, and so their inductive effects are felt more strongly in the case of molecules 1 and 3 with the closer fluorines than in molecule 2 where the fluorine is located farther away. So we should expect the acidity of molecules 3 and 1 to be greater than the acidity of molecule 2. So we're going to find molecule 2 down at the bottom of the list, and it's going to be the least acidic of the 4. But what about deciding between molecules 1 and 3? Well, in molecule 1, we only have 1 fluorine atom exerting an inductive effect, pulling electrons away from the carboxylic acid group and increasing the acidity of the carboxylic acid proton. But in molecule 3, we've got 2 fluorines doing that exact same thing, but essentially with double strength. And so because of the stronger pulling effect, the greater inductive effect, molecule 3 ought to be more acidic than molecule 1, and pKa values would bear this out. And so molecule 1 is less acidic than molecule 3, and the overall order is molecule 4 with the 5 fluorines is the most acidic, followed by molecule 3 with the 2 fluorines in close proximity, molecule 1 with the 1 fluorine in close proximity, and finally molecule 2, the least acidic, with a fluorine that's relatively distant from the carboxylic acid proton.